Okay. All right, good morning, everyone. As usual, questions from the homework. Can we do number 16? Any other questions beside that? All right. So before I start, as usual, I would like to make a comment about the quiz and the mistake that actually showed up in your quiz, because your exam is on Friday and this type of problems will be absolutely there. So what everybody did right and what usually a lot of students did wrong. So computing the ratio, which is the limit of the absolute value of an plus 1 over absolute value of an, except for very, very few students. Basically, most of you got it correct. The only mistake some students did was not putting the absolute value, which is necessary in the ratio test. And this was this piece. Then we said the series converges when the ratio is less than 1. And at this stage, we just solve it in a simple way. It means you multiply by 3. Some of you somehow did a lot of mistakes at this stage and they got a mess in their hand. And this is going to give me the x plus 4 between 3 and negative 3, causing x to be between -1 and -7. So far, the majority got that piece. And basically, I always like to draw the number line to show what's really going on. And usually the center will be at x plus 4. You can write it x minus -4. And usually this will be the center of your interval. And actually this is -4. So from here to here, I have 3 units. From here to here, I have 3 units. Now, the difficulties came up with the end point, especially one of them. So that's where some of you got issues. At x equal -1, I have to plug in the -1 into the expression of my series. And we have to simplify. So it's the sum that I'm looking at, not only the term, I'm looking at the sum. So if I plug in -1, I get 3 to the n over that, which is going to give me sigma 1 over root n. And this is one diverges because it's a p series, p equal 1/2. So that was the easy one. X equal -7 is easy, but let me point out the algebra mistake. I plug in -7 here, -7 plus 4 give me -3 to the power n over that. And it's this -3 to the power n that gave some student a headache. Let us see. I saw a lot of that. Is this true or false? Quickly. Is this true or false? Because I saw a lot of this. And this is absolutely false. Absolutely false. If you take n equal 2, the quantity -3 to the power 2 is actually 9. It's not -3 squared. So some students tended to take the minus out, which is absolutely wrong. So what is the correct setting? -3, the quantity, -3 to the power n. The correct setting is that this is -1 to the n times 3 to the n. No other correct setting for that. If you rewrite it this way, then you will not actually do mistakes. So this will become -1 to the n, 3 to the n over that. Now, this and this will naturally simplify, and this would leave me with -1 to the n over the square root of n. At this stage, we look at this. This is an alternating series where the terms are an absolute value, 1 over root n. They definitely go to 0, and they are decreasing. As n gets larger, those terms will actually become smaller. By the alternating series test, this series will converge. So the interval of convergence is going to be closed at -7, open at -1. And now that is the radius of convergence. I got a lot of bizarre answers for the radius. The radius is just in a positive number. It's a length. It's like it's the length from the center to the end point. So the radius cannot be negative. And I saw a lot of negative radiuses. It's how much you have from the center of your interval to the end point. And that's the radius, which is equal to 3. That means this is telling me that the series converge on the interval where the center is -4 and the radius is 3. It means you start from here, you go 3 units in this direction, 3 units in that direction, and that's how you get almost everything where the series converge. At the end, except the end point where you study them separately. So the main mistake occurs right there, so please be careful with this. Okay, so this takes care of the quiz. Now I go back to your questions. So, and this is the piece that I usually scan and put on Blackboard. First, the first thing I asked you yesterday is to find the power series of arctangent. All right, so let us remember it, because without it, I cannot do a lot of problems that I've assigned. So let us see arctangent, so power series of arctangent. Arctangent x. And yesterday we started it up, and I actually urged you to do it or to look at the note because it is in the note. And the first thing we were doing yesterday is the relationship between arctangent and everything of the form 1/1 minus x and 1/1 plus x. So the main thing is that the relationship is that the antiderivative of this is arctangent up to a constant. So you can always add a constant. That's really what we have. So now the idea that if I know the power series of this, integrating, I get the arctangent. So what's the power series of 1/1 plus x squared? The most natural one is to start here, plus etc. And this is going to give me the sum of -1 to the n xn, and this hold when the absolute value is less than x, less than 1, sorry. So plugging in 1 plus x squared will give me 1 minus. So I'm going to put x squared here. And this is going to give me x squared. If I put x squared here, x4. If I put x squared here, x5, sorry, x6, and etc. So finally here, I put x squared for x. It's going to give me x to the power 2n, and going from 0 to infinity. And this whole when, if I put in x squared, it means x squared should be here. X squared is less than 1. But x squared, absolute value of x squared is the same thing as absolute x squared. So this is the same thing as absolute x squared, less than 1. It means x is less than 1. So we know when everything is going to work. Now the antiderivative. So I say, okay, the antiderivative of that is equal, so integrating this means term by term integration. So that's going to give me x minus x cubed over 3 plus x5 over 5 minus x7 over 7, etc. And then we are in sigma notation in 1 minute. So now what is the arctangent? So this is the arctangent up to a constant that we take care of it in the second. It's going to be x minus x cubed plus x5 minus etc. And in sigma notation is going to be the following. -1 to the n. If I find the antiderivative of every term, we're going to have x to the power 2n plus 1 over 2n plus 1. And n goes from 0 to infinity. And now let me check if n is 0. Let me check if those coincide. If n is 0, I'm going to have x over 1. If n is 1, it's minus 2 plus 1, that's 3 over 3. Absolutely correct. Okay, so this is gonna give me the antiderivative of 1 over 1 plus square. So this is gonna give me the arctangent up to a constant. And now the constant, it's kind of bothersome. So the way we get rid of the constant, we say, if I want those two to be equal for all x's, in particular, I want them to be equal for x equal to 0. So I plug in 0 in the first piece. Arctangent give me 0 plus c equals 0, c equal to 0. And with this in mind, we are done with arctangent. And if we, every time we need to use arctangent, we have it. So I'm going to rewrite it here and work with it. So arctangent now can be written as the following infinite series. And it's sigma minus 1 to the n x to the n plus 1 over to n plus 1. Okay, and it's valid when absolute x less than 1. It means if I put any x that does not satisfy absolute x bigger than 1, and I plug it into the expression of this series, this will diverge. That's really what we have. All right, with this in mind, I'm going to go through number 16. And if you have any other question, we do. Otherwise, we move on. So let's look at number 16. Number 16, they want me to do this. They want me to find the power series expansion of the following function. So my function f of x is equal to x squared times tangent inverse is, as I said several times, another way of writing arctangent x to the power 3. So those are absolutely the same thing. So let us find those out. Now, I know arctangent. I have it, basically. I'm going to multiply it by x squared across the board and then proceed. So let us do that. So f of x equal to x squared times. I'm going to open and substitute. What is arctangent x to the power 3? I'm going to put x to the 3 in here, x to the 3 in here, x to the 3 in here. So let's do that. So instead of this x, I have to put x to the power 3 minus. Instead of this x, I'm going to put x to the power 3. If I do that, I'm going to have x to which power? Write it down. Tell me which power for x I'm going to have. To the power 9, because x3 to the power 3, don't forget your exponent. If you take in general a n, you raise to the power m, you're multiplying the power. So this is x cubed to the power 3. I multiply my power, I get x9. Plus, instead of x, I'm going to put x3 to the power 5. That's going to give me x to the power 15 over 5. So that's still in etc., which is equal to x squared times the following. So in sigma notation, I will write it. N equals 0 to infinity. Again, instead of this x, what am I supposed to put? X cubed, and then I do the algebra to the power 2n plus 1 over to n plus 1. And this holds, since I substituted x cubed for x, and this holds for x cubed less than 1, which is the same thing as x less than 1. And now I'm going to collect things in a way and simplify it, and basically I will be done. So it's just going to give me the following. Okay, I'm going to distribute the x squared here. This is going to give me x. Now, because I'm taking x squared times x cubed, I add the power. So this is going to give me x5 minus. This time that's going to give me x11 over 3 plus. That's going to give me x to the power 17 over 5 plus so on. So that's simple. I'm just multiplying term by term. Here, I'm not going to multiply first. Before I multiply, I'm going to, this is, we never leave this term like that. We definitely do the algebra here. But again, that follows a n to the power m. So it's going to give me x to which power? 3 times 2n plus 1. So right here, I'm going to have 2n plus 1, x to which power? 3 times 2, 6, n plus 3. Okay, that's what should be here. So in sigma notation, we should expect that. And now my last step in the process, I'm going to distribute the x for every term. Means basically what I'm going to do is I need to multiply. So by distributing this here, it means I'm going to multiply each one of those by x squared. I'm actually distributing exactly like I distribute over here. So now the distributing process is going to give me some x to the power 6n plus 5 over 2n plus 1, n equal 0 to infinity. And this holds when the absolute x is less than 1. Why absolute x? Because absolute x cubed means this less than 1, but if absolute x to the power 3 is less than 1, it means absolute x itself is less than. And that's going to give me the power series representation of this function. Now, before I move on, I usually double check to see, is my sigma notation here coinciding with the sum of the first two terms? So just to make sure I'm not really goofing in a way. If n is 0, that's 6n, that's 0 plus 5, that's x5 over 1. So absolutely correct. So what am I missing here? Now that I am paying attention, I'm missing something. What am I missing? And nobody is complaining. What am I missing? The minus 1 to the n. Absolutely. I am totally missing the minus 1 to the n. And I noticed this when I was double checking my work. I noticed this when I started double checking. If I hadn't double checked, I would have actually goofed. So now I go back. If n is 0, x5 over that. N is 1 minus 1, it means 6 plus 5, 11 over 3. Absolutely correct. Plus, okay, n equal to 2. I will have 12 plus 5, which is 17 over 5. I am doing 1. All right, any other questions before we move on, which is going to be a little bit along the same line, but we're going to finalize this section today. Any other questions? Number 15, okay. And I need a new paper here. All right. So number 15, I look at it. There are two ways to do number 15, and let's see, I will. All right. Number 15, I have the function f of x equal ln of 5 minus x. Okay, I'm going to find this power series, and I'm going to do it by using what we know. And what we know so far, and what you guys can use so far are the following. You can use the power series of 1 over 1 minus x. You don't have. You can use the power series of 1 over 1 plus x. You can use the power series of ln of 1 plus x. Those are some of the most fundamental power series. You can use the power series of arctangent. So, anybody have any idea how you want me to approach this problem? I'm listening, or I am hearing, or anything you want. Anybody, please? Anybody has any hint? Anything they want me to talk about? Take derivative. I can do that. It means antiderivative you want, right? Okay, I can do that. Anybody have any idea? Okay. I will do it both ways. One taking derivative, and I will sneak in another way of doing it, which is, I think it's going to be a bit more useful for you. So antiderivative, it means we noted that. If I take the antiderivative of that, what do I get? Now I have to be very careful. Do I get that exactly Yes or no? I want an answer, quick. Is what I wrote on the piece? No. What is really missing? If I make a U substitution, I definitely has to have a minus in here. Okay, so here we do U substitution. U substitution. It means I'm going to put U to be 5 minus x. And my du will be minus dx. Doing this will make this to be a minus, basically up to a constant, because that's the derivative of that. That's a constant. Derivative of the constant is 0, and the derivative of this term is this. So that's very good. Now we're going to do what we've done before. So I'm going to do it, as I said, 2 ways. That's the way that your classmate want us to do it. So I will follow verbatim. So with this in mind, I have to start with 1 over 1 minus x, because I want to hit 1 over 5 minus x. And this is 1. By now, I think you almost memorize it for those who are doing the homework. So which is sigma x to the n equals 0 to infinity. And I seem to have a problem with minus 1 to the n. And that's whole when absolute x is less than 1. Now, 1 over 5 minus x. All right, I have to relate it to this before I can proceed any further. 1 over 5 minus x, as we did yesterday, I need to factor out the 5 over 1 minus x over 5. Without factoring, aren't all the terms positive? Aren't all the terms positive? And Lori is 100% correct, and I am 100% wrong. Thanks, Lori. All right, so this is gonna be, I have to rewrite it because I need to relate it to my original. And by doing this, I know the power series of 1 over 5 minus x, which is equal to. So that's 1 over 5 times 1 minus x over 5. So this is gonna give me, in sum, so it's going to give me 1 over 5 times. I'm substituting x over 5 for x in here. So it's a 1 plus x over 5 plus x over 5 squared plus etc. And in sigma notation, that's 1 over 5 sigma x over 5, the whole thing, sorry, to the power n equals 0 to infinity. But now, for which value of x this whole? Because I'm substituting x over 5 for x, it means we need x over 5 less than 1. Means this term has to be less than 1. In a way, we know that because this is a geometric series, basically. So we know that that's the ratio, has to be less than 1. So now we're going to, I'm going to simplify this, and I'm going to integrate. So 1 over 5 minus x is going to be equal to, I will distribute 1 over 5 plus distributing x over 5 squared, distributing x squared over 5 squared, plus so on. Again, for the sum, I'm going to distribute and make it, sorry, that's x squared over 5 cubed. Again, I'm going to distribute and simplify. X over 5 to the n, it means x to the n over. When I distribute this, I will have 5 to the n plus 1. And my n go from 0 to infinity. Now my domain is going to give me x less than 5. Now I'm going to find the antiderivative from both sides and pull out my log. So the antiderivative of that is going to be equal to antiderivative of every single term. Antiderivative of the first is 1 over 5x. Antiderivative of the second is x squared over 2 times 5 squared plus antiderivative here is x cubed over 3 times 5 to the power 3. And so on. So in sigma notation, this is gonna give me antiderivative of xn is x to the n plus 1 over n plus 1, 5 to the n plus 1. my n go from 0 to infinity, my x is less than 5. Let me check before I move on. If n is 0, it's x over 5. If n is 1, x squared over 2 times 5 squared. I am most probably on the right track. So with this in mind, let us now go to the antiderivative and let's finalize this problem. So we still have one piece to finish. Okay, now we're gonna find the antiderivative, and this is where the c plays a little bit of a role, and I would take it. Shouldn't the 1/5 in the front be negative? Not yet, not yet, not yet. It's when I find the antiderivative that I'm gonna do that. What's the antiderivative of this? And now this is gonna give me minus that. Does this answer your question, Armando? Does this answer your question? Shouldn't? Yes, very good. So now the antiderivative is minus this, but we should not really be worried about it because it's a minus, so we can get rid of the minus. So the antiderivative of that is the minus ln, and now I'm not gonna write everything, I'm gonna just write a piece. So we have to keep track with everything we're doing. Plus dot, dot, dot. So I'm gonna drop the sigma notation, but I don't think it's gonna be very crucial for us. Now we have two issues. We have a minus and we have the c, because the antiderivative of this function is minus ln plus a constant, because constant doesn't really matter when I differentiate it. Now to find c, to find the constant, I'm gonna put x equal to 0 in both. If I put x equal to 0, what I will get? This is gonna give me minus ln of 5 plus c equal to 0. So this is gonna give me the c to be ln of 5. And now I will connect the dot in everything. So what I have so far, minus ln of 5 minus x plus ln of 5 is equal to this sum right there. Etc. Now I know I want this piece. So this is not really hard. I'm gonna bring the ln of 5. I'm gonna bring it right there, giving me this will become minus ln of 5 when I bring it here, and then I have to multiply across by a minus to totally isolate the ln. So finally, the ln of 5 minus x is going to be equal to this minus ln of 5. I'm going to multiply by a minus across the board, minus this, minus that, etc. Okay, so that's how we do it. If we're gonna follow verbatim what your classmates suggest, and that would be exactly and in sigma notation, it's gonna be ln of 5 minus sigma x to the n plus 1 over to n plus 1. And now I am copying verbatim from so x to the n plus 1 over n plus 1, 5 to the n plus 1, and sorry, this is n right here, n, and this hold when absolute x is less than 5. Okay. Now, before I move on, and I'm going to do this as an exercise, I'm going to assign for tomorrow, but I will have to tell you what's the other way to do this problem if you don't want to go from the beginning. So another way to do this problem is, another way. To number 15. Does anybody has any other approach before anybody has any other idea? Anybody? Okay, let me tell you another way. ln, what we've seen yesterday in class is ln of 1 plus x. We know it, okay? ln of 1 minus x. Can I figure out this one from this very easily? If I know ln of 1 plus x, do I know ln of 1 minus x easily? Yes or no? I'm not having any answers. Okay. Yes, why? I plug in minus x for x in this expression. So that's, I want to do that for tomorrow. Start with what we know. Find this one. Now, the last piece is 5 minus x. How do you think, how can I manipulate that to be able to use the one before it? I give you 2 minutes to think through before I go on. Manipulate. Because a lot of time we can manipulate, so we don't have to do a lot of work. That's why we learn the basics and then we manipulate. Can anybody figure out a way to manipulate this piece to relate it to this one? Because this is important. This is, we should know, those are important ones. Okay, please go ahead, Lori, if you know. Anybody? All right, I help you out. I have 5 minus x. I know 1 minus x. What's the game we play? We factor out the 5. X over 5. Okay? Now, of course, this 5 bothers us. But the log has very powerful properties. We know that the log of AB is log A plus log B. And now the trick. This is going to be ln of 5, which is going to capture this ln of 5 I got right there. And then the last piece would be ln of 1 minus x over 5. This one I know once I know this one. Okay, so for tomorrow, I want you guys to do it this way, to learn exactly how we try to manipulate those power series. All right? Did you guys follow the second approach? We know 1 plus x, we know 1 minus x. If I know that, this one at 5 minus x bothering me, so we're going to play the same game I played in the previous problem. Factor out the 5, will leave me with 1 minus x over 5. I know, so I split it now into ln of 5 plus ln 1 minus x over 5. If I know 1 minus x, I know 1 minus x over 5. So please try to do it for tomorrow in this approach so you will have a good practice with how to manipulate the series. Okay, so now the last piece here today, I would like to do 2 problems. And when we come back after the exam, we're actually gonna do the whole theory. It means connect a lot of dots. So before that, I would like to do only 2 problems, which are, you guys at this stage you have your notes. So one basically practical problem, and one which is how we differentiate power series. So at this stage you guys don't have to write because this is in your notes. So my question is, first let's see what the issue is. We know how to integrate. We've learned a lot about integration. And still, there are a lot of functions, that we don't know how to integrate, but not only that, we cannot express their antiderivative as a simple function. And the only way we can find that antiderivative is writing them as a series. And that's it. For example, this innocent function, 1 over 1 plus x to the power 4 dx. This is one of those functions, regardless which technique you use to find its antiderivative, you absolutely cannot do it because it doesn't work. So the only way to find an antiderivative of this function is actually one way, there's only one way, is to express this as a power series, and the antiderivative itself will be a power series. So there is no simple function that give me the antiderivative. No, none of them. The only antiderivative this function have is a series by itself. And that's one way we actually, one application of the idea of a power series. So for example, I suppose I tell you find the power series of 1 over power series representation of this integral. Because that's the only way I can find antiderivative. I really don't have any other way to do it. Now, this is not hard anymore for us because we know what is the power series of that. we know this one. By knowing this, I'm not going to write the sigma notation. I'm just going to write only the first few terms. By knowing this, I know 1 plus that, which is going to give me 1. I'm going to plug in immediately x4, x8. That's 4 to the power 3, 12, 4 plus etc. And then what's the antiderivative? 1 antiderivative. 1 antiderivative will be obtained by, actually, it's a power series. So the antiderivative, there is no other way to find the antiderivative of this function that's seemingly innocent, but there is no way. So the only way we can find antiderivative is actually that. x9 over 9. x12 over 12 plus x17 over 17. Okay, so that's one of the major application of power series, is be able to find antiderivative of function that they cannot, whose antiderivative cannot be expressed in terms of simple functions. So that's the first use. Now, question number 2, I wanted to do the following. So if we cannot find its antiderivative, we're gonna, so since the only way to find its antiderivative is a power series, so the only way to find the definite integral is actually to use the power series. Or we use Riemann sum. I mean, that's really the only way. This is an integral. To find its the definite integral, the calculator used the notion of Riemann sum. But if we cannot use Riemann sum, the only way for us to do it is basically actually express this as an infinite series. But how are we going to express it as an infinite series? So I'm going to take this, integrate, find the antiderivative term by term. So it means this is going to be equal to that. I'm just going to use the first few terms because over 12 plus x17 over 17 plus etc. evaluated between 0 and 0.5. So that's really how people manipulate those antiderivatives. And now let us estimate the value. So this is going to be equal to. So I'm estimating this definite integral. So it's going to be equal to at the upper limit minus at the lower limit. Lower limit is 0 to make things easy for us. Upper limit is going to be 0.5 minus over 5. So that's my estimate. So I'm writing the integral actually as a series of numbers. That's exactly what I'm doing. I feel I have something wrong, do I? Somewhere I should have 13 and I have 12. 13. To the power 13 over 13 plus 0.5 to the power 17 over 17 plus etc. So now the integral, that there is no way we can find an easy function. There is no easy function that expresses antiderivative. The only antiderivative it has is actually a power series. So if we want to compute the definite integral, actually we can compute it and we express the definite integral as a series. Now let us see how good this estimate is. So I'm really writing it as a series of numbers. So my question now is, use the first 4 terms. I mean, I want only this 1, 2, 3, 4. I want you to use the first partial sum to estimate the integral. What do I mean by that? I express the integral as a series of numbers now. What does it mean? It means that those partial sums should give me the value of the integral. And now I'm asking you, I only want to use the first 4 terms. It means S4 to estimate this. All right, what do I mean by that? It means I want you to take S4 which is nothing more than, so we're going to relate to partial sum. So I'm going to take S4, which is 0.5 minus 0.5 over 5 plus that. So the first terms to estimate my integral. So I'm going to take the sum of the first 5 terms. And we can do that. We can compute this using my simple calculator device. So this is gonna, I'm asking only to estimate using that. Okay, now I did compute this because I don't want to spend time, and using my little calculator, I got that much. So it means an estimate for this integral is equal to that. That's if that's just an estimate, because I used only 4 terms. But let me tell you how good the estimates is. If I use my calculator, which actually use Riemann sum to compute, the value our calculator gave us is actually the following. Watch carefully what's the value. 9.3, you guys can check my work, 5.8. So I want you to compare our estimate using only the first 4 terms to estimate this integral, how good of an estimate we're actually gonna get. And that's really how, how we use those ideas of power series. We use them to estimate, we use those partial sum to estimate quantities that we actually are very hard for us to estimate. And before I move on, something very interesting here. Something really, really interesting. And I want you to point it out. If I take this integral, and I wrote it as S4 plus there are a bunch of terms here because the integral is equal to this, all the series of numbers. So it means that there are a lot of numbers right here. How small are those numbers? Sometimes we call this the tail of the series or the remainder. How small are those numbers? Are those very small? What do you think? This integral is 0.493958. The sum, according to my computation, is 0.499576. How small is this? Extremely small, and that's important. That's really important. You're adding infinitely many terms, a lot of them. It's very, 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 very tiny. So you have infinitely many small terms. In this particular case, they are very, very tiny. This piece of the series, we call it the remainder or the tail of the series. So if a series converges, this tail is really, really, really tiny, very, very tiny if it converges. If it diverges, this piece is actually not tiny. Okay, so that's one application, one first application of the idea of a power series, something absolutely unknown to us. As using power series, you can estimate it with known values. All right, the last thing is we integrated power series. And I emphasize the integration because it has more application than differentiation. However, we can also differentiate power series. So what I'm going to do is I state here the theorem, and then I'll give you an application to that. So differentiation of a power series. It means suppose you have a function, and I was able to write it as a power series. 1 over 1 minus x, ln of 1 plus x, and so on and so forth. So I wrote it. Then this function has a derivative. And the question is, what's the derivative of the power series? So the derivative is, like we did integration, is the term by term derivative of each term. So C0, derivative is 0, so this is gone. Derivative of C1 times x, C1. Derivative of that, 2C2. Derivative of this, 3C3. So if you have a function, you know how to write as a power series. The derivative of it, its power series is the term by term differentiation. And both the original and the derivative will have the same rates of convergence. It means if the first one converges when absolute x less than r. The second will converge when absolute x is less than r as well. So I decided to give you an example, which is not the one that the book give you, but something a little bit, I thought that it's more interesting than the other one. So suppose, even though we haven't seen it, but it's a bit curious, and we're heading that route. Suppose I have a function f, and one of the use of power series is that some functions are given as power series. It means the output is a power series, instead of the output being like sine x or cosine or tangent. The output is a power series. So suppose I give you a function and tell you that f takes the input x to the following. A power series. I gave you the output as a power series. Plus so on. Okay. So my first question is, okay, does this power series converge? So you're giving me an output as power series, but is there any value of x that make this converge? So my first question is, okay, fine, when does the series converge? Because if there is no value that makes this converge, I'm giving you nonsense. So my question first is, find the interval of convergence. So basically, is there any value for which this sum makes sense? Okay, I'm going to do that. So I'm going to compute an plus 1 over an. That's the only way. The limit, it means the limit of. Now, an plus 1 in my scenario is x to the n plus 1 over n plus 1 factorial. And my an is n factorial over x to the n. With this in mind, this is going to be the limit of n factorial over that. This is going to give me n plus 1 times n factorial. So this would leave me with 1 over n plus 1 times x. As n goes to infinity, goes to 0, less than 1. And we've seen this before. What does it mean? It means regardless which value of x converges, regardless which value of x you put. Whatever x I put here, you're going to get to a number. Okay, so this makes sense for all x. So now I go back. So f of x, this function, this power series, converges for all x. Plus, etc. And this work for all x. Means regardless which x I put, the series will converge. Very good. Now I want you to find its derivative. Okay. What does the theorem tell me? If f of x equal to that, its derivative is term by term derivative. Derivative of 1, 0. Derivative of x is 1. Derivative of that, it's 2x over 2 factorial. The derivative is 3x squared over 3 factorial. 4x3 over 4 factorial. Term by term derivative. Plus, if I had x5 here, it's going to be 5x4 over 5 factorial plus so on. And this new series will converge everywhere the original one converged. It means for all x, without even computing its rate of convergence. All right, what is f prime? Let us simplify a little bit. 2x1 plus 2x over 2 factorial gives me what? X, right? Plus, what's 3x squared over 3 factorial? Anybody? 3 factorial. So I will have x squared over what here? 2, I agree. Plus, what is 4x cubed over 4 factorial? It's going to give me x cubed over what? What's 4 factorial? I can play a game, 6 You guys are correct, 6, but we're going to be a little bit, I'm going to write 6 in a different way. What's 4 factorial? It's 4 times 3 factorial. Am I correct? 4 and 4 simplify. This is going to be x cubed over 3 factorial. Plus, what's 5x4 over 5 factorial? What's that? This is 5 times 4 factorial. Sorry. Sarah is complaining. Yeah. But 2 factorial is 2. You're right. Now, 5x4, that's 5 times 4 factorial. The 5 and the 5 simplify. So we're going to have x4 over 4 factorial. If I keep the game, I'm going to have x5 over 5 factorial, etc. Okay, now I want you to watch and comment. That's why I picked this example. I want you to watch. Is there anything curious going on? Anything curious going on? Anybody? Watch. I want you to watch F. And I want you to watch F prime. I want you to watch this and this. What do you notice? What do you notice? Anything? They are the same. So F and F prime are the same. Now, which function are you aware of? Which is that has the property that the function and its derivative are exactly the same. Exactly, it's e to the x. So what we're gonna see next, basically on Monday, is that this is the power series of e to the x. It means this function here is gonna be e to the x itself. Okay, so this is the only function whose derivative equal to the function. And now the power series shows if I take f, I take f prime, they are exactly the same. And this really brings something in mind. Which function have this property? And this e to the x is the only function. And what we're going to have to basically is to show that actually e to the x could be written as this power series itself. Okay. All right. So that's it for today. Do you guys have any questions? Now remember tomorrow, of course, I will answer all your questions. And we review for the exam. So make sure you have the review with you and with your question. Okay, don't bring the review without question. Please bring the review with you and bring all your questions with you. And we discuss them. In case you don't have any questions, I will move on to basically the last 2 sections of this chapter, which is gonna tie all the ideas together. And that's it. Any question from your part? All right. If you have any problem, any questions, you can meet me in my office hours as usual. And good luck. Please work on the review. I don't know if you guys doing the review. I cannot check you anymore. Please work on the review and come with your question tomorrow. All right. Bye-bye, guys.